Guys, in the last video, I told you that in this one, we're going to talk about a new term, and it's not really a new term, actually. I mean, this is something that we've seen before, and this is going to be called void volume. So we need to go through and we need to revisit what this actually means. And void basically means empty, right? It's an empty space. Okay, so here I've got this column, and on the inside I have these particles that can now, I know, be different sizes. And now I know those particles can be made up of different functional groups on the surface of them. And now I know that in IC world, these surface areas of the particles can be positive or they can be negative. But, you know, kind of look how I've drawn them here. It's the same way that I've always drawn them. I don't really squish them all together, right? So all of this purple area that I'm coloring in, this purple area is a lot of dead space, right? This is area where a particle is not going to be located. It's an area that I have really no control of sometimes. And depending on the particle and depending on how the particle has been packed inside of that column, well, this can kind of change what this empty space would be, how much of that empty space is present. So I hope that you get the picture that there are void areas around these particles. So the void is the empty space, and that empty space is properly referred to as the void volume. Okay, void volume is going to be pretty important when it concerns a column. It's also going to depend on a couple of different things. Not only is it in the column, because this is extra dead space that your sample has to go through, but you know, we talked about the pump, right? And this pump had some tubing that goes to it and out, and to it and out. And we also talked about the mobile phase that sits up here at the top. And this mobile phase has a piece of tubing that comes out of the jug and it routes it into the machine. We also, or we will, talk about the suppressor unit. And the suppressor unit is going to have tubing that comes in and tubing that comes out. My column is sitting over here to the right hand side maybe, and I've got tubing that leads to the column, and I've got tubing that leads out of the column. And then I have a detector, and that detector is maybe sitting up here, and I've got a piece of tubing that takes my sample into the detector. All of this tubing is also going to give us void volume. So how much of it is there? That's an issue that I've got to deal with, which is also why retention times can never be textbook, right? Yeah, I can order the same column in the same instrument for the same lab. The problem, though, is that if I do two different instruments, the length of the tubing in and out of all of these pieces could be slightly different. So my retention times might be close, but they're not going to be identical values. So I can give someone an idea of what time they come off and how long they're staying in the machine, but their instrument's probably going to be made a little differently. Even if they use the same column, that same retention time is not going to show up. I could be close, but I'm not going to be identical. So the tubing is going to basically give us void volume. The column is also going to give us void volume. And then inside of this instrument, we also had that injector, right? And that injector had a loop. That loop can also give us void volume. So all of these are areas that will affect my retention time. All of these are also affecting my separation. And because of that, whenever I set up an instrument or whenever I do maintenance on the instrument, what you want to make sure of is that all of the tubing, because this you do have control of. You don't really have control of the loop. It's got to be a certain size, right? You don't really have control of how they've packed the column because somebody's done this for you already and you've just ordered it. But the tubing you do have control of. You can snip that tubing, and if you snip the tubing and put new tubing on, you want this as short as possible. And that's the reason. you're going to get rid of the void volume here. The reason that I'm talking about void volume is because the void volume is going to lead to band broadening. And you do not want that to happen. You don't want fat peaks. You want super narrow ones. So if I give it all this tubing and it's got to make its way through all of the tubing with no stationary phase in it, things could get lost in translation. They could lose their way to the end of the tunnel. And if that begins to happen, my peaks get a little bit wider and wider and wider and wider. So I need to control the road. I need to control the mileage. And by putting in new pieces of tubing, I want to make sure that I'm cutting those as short as I can. Now, I want to give it a little bit of slack, right? Just in case something has to move around, or just in case you've got to get in and do some maintenance. You want a little bit of slack on the tubing, but you do not want extremely long pieces of tubing that are just dangling inside of the ion chromatograph. It looks messy. It looks complicated. It will make your job harder, and it's also not good for the chromatogram either. So short tubing is going to lower the band broadening, and that's because there's less void volume in the system. Also, when I check for tubing, I want to use tubing with very small internal diameters. Narrow little roads is what you want them to be traveling on. You don't want them to give like a 10-lane highway. We're not Los Angeles here, okay? What we want to give them are something like a one-way street. We want something that's super narrow because we can control the traffic a little bit better. They can't venture off of the road. They're constricted on the flow path that they're going to be in, and they've got to follow the route. So if you use very small internal ID, what you would typically experience is the clump of stuff staying together, which is also very good for your chromatogram. These typically lend to very narrow peaks, very tall peaks, and that's what you want to see on the chromatogram at the very end. All right? Now, here's the truth of the matter. Most of the time, the ID of the tubing is already chosen for you by the company. So whenever you have to do replacement or maintenance on instruments, you'll order the tubing that's specialized for your piece of equipment, and that is automatically kind of set in stone by the instrumentation manufacturer, and they will send that out to you. However, some instruments, they have different IDs as far as width goes, because different tubing is used in different areas for different purposes. So you just want to make sure that you're using the right type of tubing. When you go through and you start looking at replacing some of the tubing, you want to make sure that you give them the proper item number, because not all tubing is made the same way. And you also, if you've got questions, tell the representative at the company what area this tubing was pulled from. And that will give them a better idea if you're telling them the right item number or not. So tubing can be different, just like anything else, especially on a liquid chromatograph system. And the material is going to be different. The IDs are going to be different. The pre-measured length of the tubing is going to be different. It's going to be all over the place. So just keep that in mind when you order these replacement parts and you do some maintenance on the instrument. Okay? So stay away from void volume. It's bad. And void volume is going to come to you in many different areas, and you can't control some of it, but you can control the ones from the tubing lines. And that's where your job comes in, to make sure everything looks clean, stays clean, doesn't look messy. It's not a hoarder ion chromatograph. Everything should be prim and proper in its place. All right, so that's where this video is going to stop. And in the next video, we're going to continue to talk about the column, And we're going to focus more on really the stationary phase now. Now that we've kind of went through this scenario, we've talked about the surface of the stationary phase, but we haven't talked about the actual particle itself. And that's what we'll talk about next.